Okay, let's go. Voltage difference. If we were to connect two 1.5 volt cells in series, what do you think the net voltage would be as recorded by that voltmeter? What would make sense if you go up a 1.5 volt chairlift, get off, get on another 1.5 volt chairlift? What do you think the equivalent voltage is? 3 volts. 3 volts. The total voltage in this circuit is 3 volts. The total resistance in this circuit is 10 ohms. Turns out the total current is going to be V over R. For what it's worth, just to practice analyzing this, the total current would be 0.3 amps. 0.3 amps. Why would we do this? Well, let's suppose you have a small electronic device, but it needs 3 volts to run. But you don't want to put a big 3-volt battery because that's going to be bigger than the device itself. How can you get 3 volts instead? Take two 1.5 volt batteries and connect them in series. Like this. Problem. Can you see that, Jake, my friend, as that gets bigger, what happens to your current overall? If that number got bigger, what would happen to your overall current? Go up, go down, or stay the same? Goes up. The higher your voltage, the higher your current. And the problem is current is the number of charges leaving the battery per second. This works great in that you can power a bigger device. Your batteries will burn out way faster because you're running a higher current through both of these. You got more skiers leaving. But flashlights are the classic ones that are 2 batteries in series. I'm going to guess all of you at least once in your life put the batteries into a flashlight, and you notice you put them end to end like that. What you're doing is you're getting a bigger voltage. You want a nice high voltage, a nice high current to make that bulb glow nice and bright. It's also why flashlights burn out fairly quickly. They're not well known for their longevity. You'll notice answer C says 0 volts. How could I get 0 volts in series? Flip one battery around and point it towards the other one. This is why if you put the batteries in wrong into a flashlight, nothing happens. No current flows, no voltage, no net voltage, no bulb going bright. How could I get 1.5 volts with 2 batteries? Let's come back to that. It says, explain your answer using principles of physics. I think we just did. It says, in many portable appliances, CD players, flashlights, etc. What are CD players? Shut up. 2 or 4 batteries are used in series, as in the diagram above. And in series, the effect then is to increase the total voltage. John, it's like putting a bigger battery. The negative is you're running a bigger current through both of the batteries. They're going to die faster. They're going to drain faster. Compare that with putting 2 batteries like this in parallel. What would your net voltage here be? What would your total voltage? What's the total voltage of this circuit, do you think? Well, Josh, this is like the skiers coming to the mountain and you saying, okay, I'm going to go up this chairlift, and Paige saying, okay, I'm going to go up this chairlift. You guys meet together up there. How high are you? 1.5 volts. 1.5 volts. That's how you can keep a 1.5 volt battery as a 1.5 volt battery. But if we assume that these 2 batteries are identical and therefore have identical internal resistance, what you've just done is you've split the current exactly in half. They'll last twice as long. Your graphing calculators, most of them have 4 batteries in parallel. They last quite a while. I've got one at home that's going on about 4 or 5 years, and I use it fairly often. So, parallel, you don't step up the voltage. You can't get a higher voltage. If you needed a higher voltage, you're out of luck. but they'll last longer. In fact, there are some that do a combination of both. I've seen a couple of devices where you had one battery, and then beside it, one battery. So you're stepping up that voltage, but you're trying to at least split it so that you're not draining these batteries out really fast. You've got two batteries in series, and you can mathematically treat them like one battery of the equivalent voltage and add the total internal resistors, and you get the equivalent total resistors, and then you'd have two batteries in parallel, and now it's like the second circuit. I'm sure you guys, I'm assuming you've put batteries into things before. On your test, as a multiple choice question, I will give you a question with two batteries in series, because that's, I think, the easiest situation. So I'll give you something like this, except I'll also give you an internal resistance and internal resistance, so that your total resistance is going to be this plus that one plus that one. And then I'll either say find the terminal voltage from the battery. I don't know what I'll do, but anyways, that's the only double multiple battery circuit that I'm going to give you. What about recharging? Good point. In recharging, going to your question earlier, Gabby, we point two cells towards each other. So rechargeable batteries are connected by connecting them to a cell that forces current back through the smaller voltage cell. Example 3, if we connect a 1.5 volt cell to a 6 volt charger, then first of all, what would the direction of the current be as detected by that ammeter? So where that letter A is, would it detect the current going to the left or to the right? What's downhill? Well, what's the highest hill? What's the biggest voltage in this circuit? It's meant to be really obvious, huh? 6. That's now officially downhill. So the ammeter would feel the current going from would detect the current going from right to left through it. What would the net voltage here be? 6 volts downhill, but then you have to go backwards through a 1.5 volt battery. What would make sense? What do you think the net voltage would be? What would be nice? 4.5. In fact, then I could say this, V total equals 4.5 volts, and it does say that my total resistance is 10 ohms. I guess they didn't bother us giving us internal resistors. And I can find the total current. It would be 4.5 divided by 10, 0.45 amps, and I could go from there. It says explain your answer using principles of physics. We just did, and we're about to. In terms of our ski hill analogy, cells in series, like this, are like a 2 chairlift ride to the top of the mountain. Makes sense? In terms of our ski hill analogy, cells in parallel are like 2 chairlifts, both of which lead to the top of the mountain. Shake hands and meet up. Opposite cells, well, that's like going up 1 chairlift, skiing forwards, and then going down a chairlift to get to that height. And you can technically go down a chairlift. You can ride it down, although that doesn't happen very often at a ski run. So principles to keep in mind. Positive means higher, negative means lower. Current flows downhill from positive to negative. And hopefully, I think it was in this class someone was asking, hopefully by now I've convinced you why we decide to let the positives be the ones moving even though they're not. It really makes everything else make better intellectual sense. And positive to negative means downhill loss. Negative to positive means uphill gain. Lovely physics comic. I used to do number 4. You know what? I'm going to change number 4. I'm less happy with this question. The numbers are yucky. But what I do want to do is get to example 6. This is about as tough as we're going to throw. In fact, this is tougher than physics 12. Example 6 says, find the voltage difference between point X and Y. We're actually going to do that last. Then find everything else using Kirchhoff's laws. And then I wrote, note, the complete analysis is beyond the level of physics 12. Actually, we can do it just fine. But I'm not going to give you something this complicated on your test. You ready? Let's see if we can solve.
We're not going to do number 5?
Number 5 is a continuation of number 4.
Oh, sorry.
It's okay. You just wrote a math contest. Well, tried to. So if I was analyzing this monstrosity, I'd try and see if they told me total current anywhere. I don't think they have, but I do notice they told me a current somewhere. You see it? The 0.5 amps? That gives me some direction. Also, where's the highest ski hill? What's the biggest battery? That is officially downhill, because that's the highest hill. Which means that's downhill. The current is flowing to the right through that 3.5 ohm resistor. It looks like we have current flowing this way, current flowing this way. Which way must they go when they join together? Using Kirchhoff's laws, what's my only option? Must go that way. Must go this way. Must go this way. And then we split up. Some goes up through the 4 volt and some goes to the 6 volt. Okay, I've analyzed the current directions. Now I say, is there anywhere that I know 2 things? There is. I know the current in that resistor. What's the current? It's got to be 0.5 because they told me the current right above it and there was no junctions. Okay. 0.5 amps. Josh, do I know 2? Then I know 4 things, although they didn't ask about power. So I'm going to find, I definitely would like to know what's the voltage in that resistor. Hello? What's the voltage in that resistor? I times R, 1.5 volts. And that means, Gabby, I think we can ski this ski hill completely. Megan, you with me? Okay. Here's our chairlift. How high? I don't know how high this hill is. How high is this hill? And I am still going downhill in the proper direction. So 4 volts, if that's 1.5 volts, how high must this hill be for me to be able to get to the bottom of the chairlift? Got to be 2.5 volts. Oh, I know one more thing, by the way. Or do I, Mr. Dewick? Oops, sorry, no, not yet. Now what? Hey, I see another ski run that I can ski. Because I know the chairlift, how high? Then I come to a mystery hill, but do I know that other hill? 6 volts, don't know. 2.5 volts, back to the bottom. How high must this hill be? It's got to be 3.5 volts. Ooh, and that's very nice math. What must the current be? Because now if I know 2, I know 3. Sorry? Oh, it's 3.5 divided by 3.5? Good gosh. Even Nico can do that math. After a math contest. 1 amp. Huh! I bet you now I can figure out how big that current has to be. Why 1.5? Right? I'm looking at my current flow. I got 0.5 skiers coming here, 1 coming in here. We said they all leave. That's got to be 1.5 amps. Ooh! Jaron, that means that's also, right? All the skiers go through that hill. Do I now know 2 things? Then I know 3 things. What's the voltage drop through that? Sorry, what's the resistor? Not the voltage drop. What's the resistance of this resistor? V equals IR. I guess R is going to be V over I. 2.5 divided by 1.5. 1.67 ohms. I think we've labeled every single blank. Yes? Now we have to go back and answer the original question. The original question said, hey, what's the voltage drop between location X and location Y? All right. Start here. Downhill, you lose 1.5. I guess right now I'm at negative 1.5 in my head, but I gain 4, and now I get to here. If I lose 1.5 and I gain 4, what's the voltage change? What's the voltage? What's the net voltage between those 2 points? You know what? The voltage between X and Y got to be 2.5 volts. By the way, can you see the other way I could have figured it out? Mabot, I could have said, well, if we can shake hands right here and meet up right here, then we could just go that way, and the only hill we go through is 2.5 volts. That must mean that that hill that got us to 2.5 volts. I could even have said, well, you know, since we can go this way and meet up in the same location, you gain 6, you lose 3.5. That's 2.5 volts, which also tells me the height of that middle section as well. Everything does balance up and meet up. Kind of nice. So even though I wrote, this is beyond the level of Physics 12, not really. I'm telling you, don't freak, I'm not going to give you one this yucky, but for what it's worth, Megan, by being a little clever, that was doable. That ski hill analogy really does work an awful lot. I have to thank a couple of Don Matthewson and Brent Kreitch, 2 teachers that gave me this trick. I used to teach this all mathematically using systems of equations, and my kids found it tough, and I didn't understand it very well either. So, what's your homework? You're going to get a take-home quiz. Your test is going to be a week from today, so I'll be doing a tutorial Tuesday next week after school. That doesn't work? Sorry, my other class, it worked for most of them. I was going to go Monday, but a bunch of them couldn't make it the Monday, so it's going to be Tuesday. I think I have a couple of other ones online already. I'll email those out tonight or tomorrow if you want to. But I'm also sensing most of you are doing pretty good. What's the homework? Here's what I assigned my block Bs from Lesson 7. That's Lesson 7. I want Lesson 6, Mr. Duick. I assigned 2, 3, 4, 5, 6, 7, 9, 10. 2, 3, 4, 5, 6, 7, 9, 10. Let me write that down for you guys. Easy for you to say, Mr. Duick. I assigned 2, 3, 4. Some of these are nasty. These are good practice. 5, 6, 7, 9, 10. You know what? Some of these look ugly, but some of them fall apart. For example, number 10, I was going, ugh, and then I went, hey, wait a minute. I know 2. I think just the fact that they told me 2 things there, this question kind of falls apart, because I know if that's 20 volts, I think I know how high this hill is, and now I know 2 things. They're not as bad as you think, but it's good practice. And I have for you a take-home quiz.